So this is number 10. We have the equation of a curve, which is y equals 1/6 times the quantity, 2x minus 3 cubed minus 4x, and we're supposed to find dy over dx. That just means find the derivative. So I'm going to go ahead and do that. So we're taking the derivative of a binomial raised to the nth power. So what we're going to do is we're going to keep our 1/6 out here. We multiply our 1/6 by our current exponent. So there's the 3. And then we multiply that also by the derivative of the inside. So this is the chain rule. What's inside stays the same at this point. And the last thing we need to change is the exponent. So it becomes n minus 1 or 2 minus 1. Okay? Our outside is just a term on its own. There's nothing fancy. So we take the derivative of negative 4x, which is negative 4. So when we simplify, we end up getting 6 times 1/6, which is 1, okay, times the quantity, 2x minus 3 squared, minus 4. Okay, alright, so that is I. And now what they want us to do is they want us to find the equation of the tangent to the curve at the point where the curve intersects the y-axis. So, where anything intersects the y-axis is the y-intercept, and we know that all y-intercepts have an x-coordinate of 0. So the first thing I'm going to do is I'm going to find the y-coordinate when x is 0, or the coordinate of the y-intercept. So I'm just rewriting the equation. So basically everywhere, my pen isn't writing very well. Alright, everywhere I have a x, I'm going to replace this with a 0. So I end up with 1/6 times negative 3 cubed minus 0. Okay, so that's completely unnecessary. So I end up with negative 3 cubed is negative 27 times 1/6. So y equals negative 27 over 6, which is also equal to, if I divide both by 3 to get a common equivalent fraction. Oh, this pen. Alright, negative 9 over 2. Okay, so either way you'd like. Okay, so that's the y coordinate. So I'm going to say negative 9 halves. Okay, and now we need to find the slope. So if you'll remember, the slope of the tangent occurs at a given point, and is dy over dx. So I'm going to go ahead and sub in. Okay, this was supposed to be a 2. I don't know what happened there. Okay, so I'm going to go ahead and sub in 0 everywhere I see x. And that just happens to be in one place. Minus 4. So we end up with negative 9 squared minus 4. And that equals, sorry, negative 3 squared minus 4. So that becomes 9 minus 4, which is 5. So part 3 says, find the set of values of x for which 1/6 quantity 2x minus 3 cubed minus 4x is an increasing function of x. Alright, so at this point we need to find the stationary values as a start, because increasing and decreasing happens to increasing and decreasing values happen when you know what the stationary values are and you can find which way your curve is turning. Okay, so I'm just rewriting, oh, not that, I'm rewriting the derivative. I ran out of room, so I'm rewriting it. So it was 2x minus 3 squared minus 4. Okay, so that's y prime, or dy over dx, as this problem has called for. So I'm going to basically find the stationary points. So I'm setting the derivative equal to 0. And now I'm just going to solve. So I end up with 4 equals the quantity 2x minus 3 raised to the power of 2. At this point, I'm going to square root both sides, and just as a reminder, since I'm the one square rooting, I don't know if it's 2 times 2 to make 4 or negative 2 times negative 2 to make 4, so I'm accounting for both. Okay, and now I'm going to add 3 to both sides. So that leaves me with 3 plus or minus 2, and then I'm dividing by 2 on both sides. So my first stationary point has an x-coordinate of 3 plus 2 is 5 over 2, so 5 halves. My second stationary point has an x-coordinate of 3 minus 2, which is 1, divided by 2. Okay, so those are our stationary points. At this point, you could do several things. You could use the second derivative to find out which one's a max or a min, and then you would know where it's increasing or decreasing from. Or you could use an interval table, and I'm going to do that here because I think I just want to show you how to do this in a different way. So 5 halves. Okay, so I'm putting these in order from least to greatest, and I am basically going to plug in a number that's smaller than half for this one. So my favorite number to plug in when that's the case is 0. So we did that with when we were finding the slope at 0. So we got positive 5. So I know that this is positive. Okay, so it's increasing here. Because the second derivative tells it, or the first derivative can tell us where we're increasing, decreasing. Okay, so I'm going to pick a number between half and 5 halves. The number 1's a nice one. So 2 times 1 is 2 minus 3 is negative 1. So we have negative 1 squared minus 4. So that still is negative 3. So there's a negative. So we're decreasing here. Pretty good bet that we're increasing over here, but we're just going to check. This is really 2.5, so I'm going to plug in 3. So 2 times 3 is 6 minus 3. Then we square that. Minus 4. So that's positive. Okay, so basically, I'm increasing when x is less than half. And remember, we don't include half in this because this point is neither increasing nor decreasing because it's a stationary point. It has a slope of 0, so it's just being steady there. Okay, and x is also increasing when x is greater than 5 halves. Okay, if you wanted to do this with the second derivative, or I'll show you how to write it in one more way. If you wanted to do this with the second derivative, you'd find out which are the max and mins, and then you can write the increasing and decreasing functions based on those. It's just kind of a little extra step process, or thought process, not step process. Okay, if you wanted to do interval notation, it would look like this with both parentheses, because neither negative infinity nor half is included. And the same goes here. Okay, so that's how you would do that in interval notation.